So let's start. Hello, everyone. My name is Alex Senderovic. I'm from the University of Toronto, and it's my honor and pleasure to chair this third session of EDBA. This session is about event abstraction, trying to fill the gap or mitigate the mismatch between the granularity of events that we see in logs and the desired level of activities and process models. Our first paper is going to be presented by Dominic Janssen on process model discovery from sensor event data, a topic I'm very curious about. Dominic, the stage is yours.
Thank you, Eric, for the introduction. As you already said, I will be talking today about process model discovery from sensor event data. My name is Dominic. As you also already said, I will be speaking here representing also Felix, who's here as well, and Agnes, who is here as well, and Buzz, who is hosting another event and is excused. And let's jump right into the research question. So the question is, can we express daily habits in a process model by only using low-level event data? There is an asterisk attached to it with so many things. We can, but we need a map in addition, which is not that big of a problem. We just need to keep that in mind. The setting we have is centered around the CASAS dataset. Most of you will be familiar with those datasets. It's publicly available. Smart home datasets with different types of sensors equipped, different amount of people inhabited those houses for different amounts of times. We chose one that has 2 inhabitants and looks like this. That's the floor plan of the house. It's equipped with a lot of sensors. We only look into motion sensors for our research right now. They are highlighted here in green. And the data we're dealing with is unlabeled data. So all that is recorded is whether a sensor is activated or not, and the date and the time associated with it. Our starting point is a smart house. In our case, could be a smart factory, could be anything, as long as it's like a spatial thing, equipped with sensors. In our case, motion sensors. Could be any type of sensors. They only have to be able to detect the presence or absence of things or people. That brings us to our last thing we need, that are the very people we want to observe. And what's our desired goal? We want to find a process model that can represent some daily habits. The question is now, how do we get here? And we came up with a framework. It all starts with the location sensor event log. That's what I just mentioned, the data recorded by the smart house, by the smart home, is whether a sensor was activated or not, the name of the sensor, and the time when that happens. And because we do have a map, we can then know where that very sensor is and have spatial information and can calculate distance between those sensors. That gives us our entry point for our framework, the location sensor event log. Next up is the event case correlation. So we have the location sensor event log, and from there we want to associated cases with it. And we end up with an activity instance event log. How do we do that? There's a to-do list we need to take care of. We want to make sure that there's only one person per case, and we want to make sure that there's only one activity per case. Why is it so important that there's only one activity per case? Well, we later want to cluster those cases, and if there are multiple activities in one case, we might run into a problem. So we want to make sure that there's only one single activity in each case. Our first point on our to-do list is the entity detection. So there's a scenario where entities are far away from each other. So we have a part of the house here, and there's one person in just a regular room and another person is in the bathroom. They're far apart from each other. Just by calculating the distance between the sensors in play, we know there's no way one single person could activate those two sensors at the same time. So we know that has to be two people. So that one is fairly easy. Then there's the second scenario where entities are close to each other. That could happen anywhere, but narrow hallways are a very good point where that could happen. So right here we have the hallway. On the left there's stairs, on the right there's just a regular hallway. And then there we have two people. They're standing beneath one motion sensor. And since motion sensors only can tell us if there's something beneath it or not, we cannot say, is there one person, is there two person, is there two people? There's no way we could know that just from looking at the sensor data at that very moment in time. What can we do about it? We can sort of travel to the past and look what has happened before. And there was one point, like a few moments ago, a few seconds ago, where those two people were indeed very far apart from each other, so that we know those sensors, they activate, they're a certain distance away from each other. There's no explanation, or it's not possible that a single person can activate those two sensors that far away from each other. And then as we move on in time, we'll end up at the scenario where those two people are gathered just beneath one sensor. And as it's indicated by the slightly faded out pictograms, we'll just keep in mind that there were two people before, and now we only have one sensor registering motion, but we know there were two people before. So we'll just assume that the person did not just vanish, and we know that two people are still there, and they are there under that very one motion sensor. And then as time moves on, they continue their motion, and we then are able to separate two entities, even though they are very close to each other at one point. We did do a simplification there. We assumed that they keep the direction of movement. So they're heading the same way they were before their rendezvous. So that is a simplification we did. That is, at that stage, our research is in right now a somewhat okay solution. So we can tick it and can say, yeah, we can make sure that there's only one person per case. Next up, there's one activity per case. So we'll call this sensor case slicing. So we have a person moving around the house like this, generating a lot of events. And now the question is, where does an activity start and stop? Possible factors could be the time, passage of time, or rooms. Certain activities are bound to certain rooms, so cooking can usually only happen in the kitchen. There could be factors. We settled for a slightly simpler approach and just cut the traces at a fixed length. Another simplification, but just because we're trying to prove a concept here that we can go from raw sensor data to a process model, we can get away with that for now. So we'll just take the trace and cut it at a fixed length into small cases. So we did our two to-dos, and we're moving on to the next point, that is activity discovery. So we have the activity instance event log we just created with the cases, and we want to cluster those similar cases now and find an activity label for each cluster. And that gives us the process activities. There's things we need to do, obviously. We need to do the clustering and we need to do the labeling. So for the clustering, we use two machine learning algorithms. The one is the k-means algorithm. It's a very simple one. Probably everyone knows about it. And we use that as a baseline to just compare if using a little bit more fancy machine learning algorithms is worth the effort. And the little bit more fancy version of a machine learning algorithms we use is a self-organizing map. And indeed, we found out that putting a little bit more effort into the clustering yields better results. So self-organizing map is the way to go here, at least compared to the k-means algorithm. There was one thing we need to keep in mind when working with those two algorithms, is that both require calculable Euclidean distance between vectors. And that's a problem because the vectors look like this. There's arbitrarily given sensor names, and there's no way we can calculate a meaningful Euclidean distance between sensor M46 and M26. So we did do a workaround. We counted the number of activations in a vector and compared those to each other, calculated the distance between them, and we counted the duration each sensor is activated. Those are two approaches. And then the third one is we do both, where we just use a vector that is twice as long, that contains both the number of activations and the duration each sensor is activated. And our experiments show that using both gives us better results when clustering. So we did that, and then the next step is the activity labeling. So this is a little tedious because we need to inspect the process model for each cluster. The more clusters, the more work. So we have a process model here, exemplary, simplified, and we'll look at the floor plan at the same time and just see what sensors are involved. And we see it's the bathroom, it ends at the shower. So we'll just make an educated guess and say, person is showering here. The drawback is that this is a manual step that is required. The good news is that is the only manual step required in our framework. So we did all the to-dos for our process activities. Now we want to continue with the event abstraction. For that, we take the activity labels we just found and merge them together with the cases we found earlier and come up with a process event log. And in that process event log, we have the activities, we have when they started, when they're completed. We have the information which entity is responsible for which activity. So that's a good starting point for the process discovery, which is the last step in our framework. So we'll have the process event log I just mentioned. And as a result, we want to have the long desired process model. And we need to do some additional steps, of course. We cannot just get it. There's two more steps we need to do. We need to find a suitable starting activity, and we need to apply a mining algorithm. And where could be a start of a routine behavior is a question we have to ask ourselves, and we do that by looking at the floor plan and make an educated guess again. And I'm going to highlight the interesting parts here. There on the right, you can see the circles that are doors. So we would assume that if someone comes home, enters the door, then they start their routine behavior. So when you come home from work, you would start making dinner, well, maybe wash your hands first, but then make dinner, eat, watch TV, and so on. So that could be the start of a routine behavior. And then another possibility is, of course, everyone knows it, when you wake up, you usually follow a very similar morning routine. So after sleeping, you wake up and then you have usually a routine behavior. So those could be good starting points for routine behavior. So we did that, and now we need to apply a mining algorithm. A suitable mining algorithm, there are many out there. We used the heuristic miner. Why did we settle with that? Because heuristic miner is suitable for infrequent behavior. So even though some people might have a very tedious morning routine, there's always little variations, because after all, it's human behavior, and at home you usually don't follow a strict workflow. That's why the heuristic miner seems like a good choice here. So that's the last point on our to-do list, and that concludes all the steps that are necessary for the framework which we came up. So on the left here, you have a location sensor event log from raw sensor data, And then on the right, you have the process model, which we wanted in the beginning. So that brings us back to our introductory research question. Can we express daily habits in a process model by only using low-level data?
Dominic,
and the answer is yes. The answer is yes. Otherwise, I wouldn't be standing here if it would be complete garbage. And but there's also an asterisk there. There is still a lot of work to do. We could improve entity detection. Variable trace length should be something we have to look into. Fixed trace length is obviously not ideal because different activities have different lengths. We could include spatial information, so where the activity happens, in which room. We could apply other machine learning techniques. We could apply different minors. We could include temporal context. I could go on and on. There's a lot of things we still need to explore. And that's what we're going to do in the months to come. And the code is publicly available of the framework on GitHub. And I'm happy to answer some questions. My associate Felix is here. My supervisor Agnes is here. They will also be happy to assist me with the answering of questions. And if something comes up later, just email me and I'll get back to you.
Thank you, Dominic. Let's see if we have questions. I don't see anything in the chat, but the audience or the participants, feel free to raise your hand and I will monitor this. Let's see. Any questions? All right, Benoit, you go ahead first.
Yes, thank you, Dominic, for the work and for the presentation. I have to say it seems quite impressive considering where you start from, the kind of data you have all the way to trying to discover habits. And there are a lot of steps in between that you go through. I do have some questions though with respect. You in the beginning of your presentation, you said it seemed as if you wanted to learn a discovery model. So you're going from these low-level center data up to activities, then to clusters of activities, such as you can make an event log, and then you want to learn a process model. Do you really think this is the best? I mean, why would you need a process model to discover habits? Why would you go for a process model and for process mining? I think all these steps, I mean, I think it makes sense, but I'm just not personally not convinced that that process mining and discovering process models, what the kind that the current discovery algorithms typically give us, is what you would really need as a technique. But what's your opinion on this, or your experience on this, the models you got out of it?
Well, I'm guessing you wanna say that it's very difficult to find a process in daily human behavior in a house.
Well, I'm wondering, you did the exercise. Let me rephrase it a little bit, because I don't want to say, to what extent did the heuristic miner gave you a model that gave you true insights into the habits of people? What was your experience with this?
It is a little bit like reading the, I don't know, if you drink tea and you have the leftover of tea, and so some people could say, oh, you see what you want to see. So that's why I can deduce behavior from the process model that was discovered. But we were assuming for now that the resulting process model isn't as clear as we hope, is because we did do so many simplifications in the beginning. So our entity detection doesn't work that well. It works sufficiently enough to show that there could be benefits from using the heuristics miner, but that is yet to be seen. So yeah, that's a valid criticism. It just has to be seen.
Just to be clear, okay, make sure. It was not mentioned as criticism. I think what you're tackling is a very challenging problem. I sometimes think that if you do this, you have many terms like events, activities, behaviors, and habits, which are actually are not the same thing. So we have to really think about what does represent, and we have to be careful, I think, as a process mining community, to not try to use the tools we have developed always on this. I think it's a good start, but I think we will need to find other ways to look at these concepts if we really want to think. But I like the work, certainly.
Okay.
Yes, Felix, go
Can I
ahead.
just add a little bit? I think it's just one thing we also thought, of course, is in a way where process mining could give a real difference is to have these interleaved or parallel things where you, of course, if it's habits of one person, it will not be parallel because we're inherently like sequential beings. But that you sometimes start there, sometimes start here. So I think one thing that we, for example, I think discussed to look in the future is also that there's this work from Nick Tux on local process models that would make a lot of sense to compare against or integrate in here. So, but yeah, it's of course challenging even to find in an mainly unsupervised way to find something.
So I have a follow-up answer to Benoit. We've been actually working with similar data that's coming from a hospital, and there you want to understand patient flow, and that's exactly sensor data following patients and so on. So this application to daily habits. You can easily take that and apply it to a hospital setting or to other settings, airports, where you track the location of your entities and trying to figure out what is the business process they're following. And that leads me to my question, Dominic. Did you see the work where I'm also co-authored with Andreas Rogesolti and Victor Gal, who is also here in the participants, where we take low-level events from a hospital and use an optimization approach to reach exactly the high-level abstraction you're talking about. It's called the road. I think Felix knows that work.
Yeah, Felix nodded. I can't tell you off the top of my head right now if I've read it.
But this looks something your daily habits problem is something that the approach can.
Yeah. I think. Yeah, we knew it.
I think you took batch data of employees, didn't you?
No. It's exactly the log you start with the locations and the sensors. It's exactly our starting point.
Yeah.
And then we match it against, similar to how you say that that the sensor is a kitchen. We know that the sensor is an exam room. And then we do the matching. And except we don't use clustering, we use optimization, but it's the same gist.
Yeah. And you try to mine the interactions, kind of. You give more semantics to the individual locations, right? So
yeah. But the framework is general enough to also have single case, even if you don't have interaction.
Okay.
And the implementation is available. So just all right. Let's move on to the next speaker. If there are no further questions from the participants. Our next paper, Greg, you want to share screens? And let's thank Dominic again for the great presentation. We will have an option to clap here. Yeah.
I do think Dominic needs to stop sharing.
Yeah, you need to release.
I'm doing my best.
Take your time. All right.
Great. Whenever you're ready.
Very well.
So,
yeah. Hello, everyone. My name is Greg van Hout. I am a PhD student affiliated with Hasselt University. And together with my colleagues Benoit de Pere and Niels Martin, I would like to present my work on event abstraction in a process mining context, a benchmark study. Now, to give a little bit of a background, we're all working in process mining, and that means that we are working around processes. And these processes, they typically generate a lot of data. Either it's automatically generated or manually logged, but in the end, we end up with event logs based on these processes. And after applying process discovery techniques, we end up with process models. Now, unfortunately, often these process models, they tend to be a bit like spaghetti models, with which I mean they can get very big very quickly when the process displays more behavior than just the happy part. Now, for example, the fuzzy miner, it has implemented an edge filtering technique to reduce that process model to a more simple representation of the process by filtering out the infrequent behavior. Now, this work tries to accomplish sort of the same thing, but we're going to go the other way around. We're not going to manipulate the process model directly. Instead, we're going to say that we have discovered some interesting patterns in the process. Often these patterns frequently occur, and we're going to call them event abstraction patterns. Basically, we're going to substitute these patterns into the event log by just one single higher level activity. And that's the goal of this work. This work will investigate the effectiveness of using event log abstraction with these unsupervised event pattern miners to reduce the complexity of the resulting process map. Now, how are we going to do that? Well, first of all, we need to define the problem class. And the problem class, it is as follows. We start with a very complex process model. Why is it complex? Because it's often generated based on a very fine-grained event log. So again, we're going to manipulate the event log instead of doing filtering techniques on the process model itself. We're going to augment it with these higher level activities and try to accomplish the same thing, a more simplified process model. The end goal here would be to reduce the complexity, but of course, we still want the new process model to represent the underlying process adequately. In other words, ideally, the fitness and precision values, they would be maintained. How are we going to evaluate our approach? We have defined 5 steps in this experiment. First of all, we're going to start with the low-level event log and start mining the event abstraction patterns. How we're going to do that, I'll explain in a minute. Step 2 would then be to construct the high-level event log. Again, we're going to insert the higher level patterns into the event log. We're going to do that on a pattern-based approach as designed by Felix Manhart et al. Next, having obtained the higher level log, we can construct the higher level process model as well to start computing complexity metrics. When obtaining the new complexity metrics, we can then make the comparison between the higher level and the lower level process model to see if there's an evolution. However, complexity is not the only thing here. We're also considering fitness and precision, but at this moment, we cannot compute these values yet. Remember, we are inserting new higher level patterns, which are not present in the original low level event log. So the mapping is incomplete. To that end, we'd have to expand these abstracted patterns, which we have readily available anyway, back into the high level model so that we have the full complete mapping again. Once that is in order, we can then calculate new fitness and precision values. You'll recognize this evaluation method based on a work from Manhart and Tax, where they did a sort of the same study with local process models. And that's also our own starting point when it's about our experimental design. When it's about the abstraction pattern miners, we're also considering local process models, but we're adding combination-based behavioral pattern mining, or LPM and COPAM for short. Now, why have we limited ourselves to these 2 techniques? A very simple reason, actually, because they define a process between the low-level events in the event abstraction pattern. It might seem odd that I say that they define a process, but that's actually what I mean with this process map of the pattern itself. Instead of just saying, like event clustering techniques often do, A, B, and C belong together, these 2 techniques also tell us how they belong together. A is followed by B and C in parallel, and B can be looped, for example. Now, experts in the fields might think, well, okay, LPM, COPAM, yes, they fit your definition, but what about the RefMod miner? The RefMod miner is also discovered in our literature search, and it is one very good advantage in this story. The RefMod miner, looking for reference model components, as they call it, or subprocesses in another term, they are actually guaranteed not to have overlaps with each other, and you can stack them up in higher levels as well. So in our study, it would fit in perfectly. Unfortunately, the implementation was not publicly available, so we could not include it in our study. Next up, once we have mined the abstraction patterns, we're going to transform the event log. How are we going to do that? We have selected the top 3 non-subsumed patterns. Why is that important? Because LPM, for example, it's quite possible that they give multiple patterns, like the sequence of A followed by B, but also the sequence of A followed by B followed by C. The first one is subsumed by the second, so it would not make sense to insert both as input for the algorithm. How are we going to measure the quality? We're using the alignment-based fitness, the ETC precision values, and a combination of 10 complexity metrics, so 12 metrics in total. Moving on to our empirical results then. Again, this study will focus on 2 aspects, trying to reduce the model complexity on the one hand, and trying to maintain fitness and precision on the second hand. So also our empirical results will be based on these 2 perspectives, starting with the effect of abstraction on model complexity. The 10 metrics that we have chosen for complexity are the following: cognitive weight, token split, connector heterogeneity, etc., etc. And previous research has actually shown that these metrics can be divided in 4 dimensions. Now, there are many more complexity metrics available in the literature than these 10, but these are the 10 that we thought suited best for our technique. Now, from a very broad perspective, investigating our results, they were either negative or mixed, in the sense that for 2 of these 4 dimensions, cognitive weight is a bit on its own, but 2 of these 4 dimensions actually reduced on average for all of our combinations of experiments. While cognitive weight showed mixed results, the diameter showed mixed results, depth showed mixed results, and density as well. And these are the 4 complexity metrics that we're going to investigate further. However, first we aggregated our experimental results, but we were surprised with the outcomes. The outcomes were not as we expected. Why? Because the results seem to be more influenced by the process discovery algorithms than the event abstraction miners actually. I'm going to illustrate it. You can see the 4 metrics to the left divided by LPM and COPAM, the abstraction pattern miners, and the split miner inductive miner. Do consider a negative delta here is an improvement because we want to reduce complexity, of course. And we can see that cognitive weight, it's a reduction in complexity with the split miner, but an increase in complexity with the inductive miner. The same thing for depth, but then for density, it was the other way around all of a sudden. There, the split miner showed an increase in complexity and the inductive miner actually a reduction. And diameter, well, with our experimental results, we cannot even see a clear correlation with either type of miner. Why this is happening? Well, perhaps for cognitive weight and depth, we can say, okay, the inductive miner often uses parallel gateways to model the parallel behavior. So perhaps that's one of the reasons that the complexity there increases after abstraction. The split miner tries to simulate sort of parallel behavior by looping back to previous steps in the model. Therefore, maybe density increase after abstraction. But this is uncertain at the moment. This still has to be investigated further. What we can say, however, is that we consider all of the experimental results at the same time from the broad view. We can see that there are 15 improvements in total when using local process models and 19 improvements in total when using COPAM. A very important side note, however, we have used 3 patterns at this moment, but what happens if we use more? Because one could expect the more activity patterns we insert in our algorithm, in our experiment, the better the complexity would be, because we're actually hiding more complex behavior. Do note that this could, of course, also have an impact on fitness and precision. And when talking about fitness and precision, we have very clear results here, but again, not really the results that we were hoping for. In the sense that when we take a look at fitness, in combination with the split miner, there was no increase. When it's about the inductive miner, only once. And for precision, inductive miner 2 times. But when you look at the average deltas, it's always a pretty drastic increase. The one thing that, decrease, apologies. The one thing that we do note, however, when looking at precision in combination LPM and split minor, on average, there's an increase, which was quite surprising, actually. I'm going to get into that later. But again, when we first consider all of our results in general, LPM shows 6 improvements, mediocre, but yeah, the deltas pretty much still say enough. There is a hit in both metrics. COPAM only shows 2 improvements. Now, when zooming into the precision, there are some important questions that we have to ask ourselves. What is the reason that LPM cannot reproduce the results with inductive minor? Well, after investigating the models, our intuition shows that perhaps it is because the split minor often tries to look for the best fitting models, in the sense that the baseline must also near perfect in most of our cases. And of course, precision has to be sacrificed for that. So maybe because we are expanding the model after learning it with a split minor, we're kind of enforcing the split minor to search for that balance because it can no longer accommodate for that expansion to create again the best fitting models. The second question we have to ask ourselves, why can't COPAM improve precision on average like LPM can? And maybe here the reason lies in the very fundamentals of the COPAM technique. COPAM always looks for the compact maximal patterns. And we believe that it's in the maximal part of the definition of COPAM patterns, which dictates that a pattern will be expanded with more infrequent or even infrequent behavior. And we have observed this in the hospital billing log, in which we saw that in each of the 3 patterns that we mined and used with COPAM, the event delete was added in a choice operator. And when investigating the event log, delete only occurred in about 1.4% of the total events, which is very infrequent. And all of a sudden, after expansion, it was present 3 times in our event log. So of course, that will indicate a hit on our precision, without a doubt. Now, what can we conclude from this experiment? Well, first of all, when taking a look at fitness, it typically takes a hit. It only rarely improves. And it's also very clear that the split minor shows the greater loss here. Now, is a reduction in fitness really unexpected? I would say no. The goal of event log abstraction is indeed to hide complex behavior. And as expansion, after inserting the pattern, it can no longer be accounted for by the minor. So of course, we can expect a hit in fitness. When looking at precision, on the other hand, we see an average increase in the values at LPM and split minor. We believe, again, that this may be due to the fact that the split minor tries to sacrifice precision for fitness. For COPAM, well, okay, it's faring pretty well, slight reduction, but still, maybe the problem here is with the maximal patterns. And COPAM could be designed for more meaningful patterns in the basis, but that doesn't mean that's also better when used in event log abstraction. Finally, as for complexity, yes, most metrics tend to decrease, but on the other hand, there is no clear and uniform impact. We were hoping for a decrease in model complexity, and we don't believe that we really accomplished that. Now, it wouldn't be a benchmark study, of course, if we didn't try to declare a winner. But can we declare a winner? I mean, again, there seems to be a very clear interaction between the event abstraction discovery minors and the process discovery minors. So can we really see it in an isolated fashion? Maybe yes, maybe no. What we can say is that if we want to focus on fitness and precision, and especially precision with a split minor, if that is your focus, opt for the local process models in your abstraction. On the other hand, if you try to reduce the complexity, and even though it's only by a small margin, COPAM will have the small edge. Now, what are the different limitations of our study? Of course, no study is perfect. First of all, we have used a very naive scoring and selection of the event abstraction patterns. We've only selected the top 3 non-subsuming patterns, but recently work has been introduced with a more advanced selection patterns for LPMs, and perhaps that work can also be expanded to COPAM. Next, we have used a fixed number of patterns. Increasing it from 3 to 5, 10, or 20 could potentially have a positive impact on the complexity, but also potentially a negative impact on fitness and precision. Next, we've only used 6 event logs at this moment. Perhaps increasing this number could have provided us with more certainty and clarity about how the complexity metrics would evolve, because right now there is a lot of uncertainty, especially with the diameter metric. And of course, as already mentioned, we must really include the RefMod miner in future experimentation, just to see if the advantage, which I stated earlier, really is an advantage also in event log abstraction. With that, I would like to end my presentation on the event abstraction work I have done with my colleagues. If you have any questions, feel free to ask them right now. I'd be more than happy to help you. And should it be necessary, my colleague Benoit is also here. So Benoit, feel free to jump in if you want. Thank you.
Thank you, Greg. Let's see if we have questions. Feel free to raise your hand. Felix, are you raising your hand?
Yes, I didn't find where to do it in Zoom, if I may.
I expected you to ask a question, Felix.
Yeah, so thanks I don't have much time, unfortunately, but thanks very much for doing this research. It's very interesting to see that this is continued. One question I have, because that was the main question we got when we wrote the paper, is have you any idea how to kind of make sense of the patterns you get and the models? Because I mean, we also showed in this paper that you can improve precision or trade off things.
Mm-hmm.
But then, like on a qualitative level, what does it actually mean? It's maybe also related to the question we got for the last paper, for the last presentation. It's kind of, okay, you have these patterns, but how to make sense of them?
Yeah, I've been wondering about the same thing indeed, because when you use LPM and COPAM, you often get dozens, hundreds of results even, and you see a very close resemblance between them. So the selection between them, not only from the abstraction viewpoint, but also the semantic viewpoint, I'd say it's very vague at this moment, because we've been trying to work in the unsupervised context, but at this moment, the top 3 in frequency, who says that these are the perfect patterns? I mean, for example, a domain expert could have said, well, yes, okay, this might occur frequently, but these events actually have nothing to do with each other. And I believe it's very difficult to determine that in a completely unsupervised context at this moment. So I believe that you have obtained the same question in your research with LPMs.
Yes.
Yeah, maybe I can add to that, Felix. I think what you did, you came from the other way around, right? You started with like domain expert providing these experiments, and then the question was, of course, can we use an automated technique to actually discover these patterns like computer scientists like to do, automate everything, and we don't need humans anymore. I think I personally believe that if you want to make this work, you will need some kind of interactive approach where you discover patterns that can be modified by domain expert to make them more sensible. With this research, this was like a first step in the research, just to get an idea about, does it even work? And can we even get to the point, even if it doesn't make sense, we would expect complexity to go down, or actually understandability to go up, and we use complexity as a proxy. But of course, not at the cost. I mean, there's always, I think, going to be a trade-off against fitness and precision to some extent. You can make it very simple. You say, okay, I have a flower model with all my activities. That's my pattern, and that represents activity X. And I can just, every trace becomes activity X, and I have a a great model, very easy to understand at first sight. But if you go back to the original event log, yeah, precision is terrible because you actually have a flower model underneath. So that was just to get, the idea of this study was mainly to get insight. How does it currently perform? Which are the weaknesses? And I think one of the things that we found, we tried to find explanations, but it was very hard. But one of the things that we find interesting to see is that there is this interaction between the miner and the kind of models they typically produce and the abstraction technique. And I think a key takeaway is that if you want to develop better abstraction techniques, don't ignore the kind of minor you have to apply them on. You have to, I think we really have to understand this interaction before we can make better abstraction techniques than we have currently. But to go back to your final, in the end, to make it meaningful, I think you will always need a human expert in the loop.
Yeah, some interactive thing or so.
Yeah.
I discovered in the original work on the supervised weight, I mean, the reason it really worked was mainly also to take away parallelism in a way, and that can have maybe a big effect there. Because that was in this guided process discovery, I called it, it was actually the fact is if you kind of have a pattern that takes away some things that can happen in parallel with the rest, and for example, in the sepsis data set, that's in this data set, then it really helps inductive minor because yeah, it doesn't need to do this anymore to detect this.
Yes.
And yeah, okay.
Thank you for your question.
Thanks for the question, Felix. Do we have other questions? I think we're right on time to close this session. I would like to thank the speakers again, Greg and Dominic.
Thank you. I'd say if anyone has any other questions, you can see my mailing address on the screen right now. Feel free to send me an email. All right.
Thank you. And with this, we're closing the third and final session. Benoit, any last comments? Shall we close the workshop?
I would say thank everybody for attending this
Thank you so much, everyone.
workshop. Yeah, sure.